Hello and welcome to this presentation about Tink, a temporal graph analytics library for Apache Flink. For the last 6 months, I've been working on Tink for my graduation project that I did at Eindhoven University of Technology. And with this, I conclude my master's that I did here at the TUE. So, Tink. Tink is a library for Apache Flink for temporal graph analysis, and in this next 30 minutes I hope to explain the usage of it and what it can do and which results were obtained during that work. I will start by explaining a use case, which is one of the thousands of things that you can actually do with this library and with this type of analysis. Then I will explain more about the temporal graphs, followed by Tink and Tink's algorithms. I will continue with the results and finally end with the conclusion of this work. So, the use case. In here you see a map. My dad came to me a year ago, because he was traveling every day from Breda to Arnhem for his work, and he kept getting stuck in traffic jams. And he wanted to have something to avoid these traffic jams. So I installed Google Maps for him, and with that he could navigate and bypass these traffic jams which occur. This is one of the routes that you see here, which you see if you leave around 7 a.m. from Breda. And you will see that there is a small traffic jam here and a small traffic jam at Os over here. But when he took this route and he arrived at Os around 7:35, this traffic jam at Os has grown immensely, which resulted that when he would have taken the other route, this one, which has a traffic jam at the start but no traffic jams at the end, he would have gotten at his work faster. But when you only look at the current data, you wouldn't be able to see such a thing. While if you look at the temporal data, which takes into account that different things happen at different times, you would be able to analyze this. So in the Netherlands, we have the AMB prognosis, which can predict these kind of traffic jams. And we can also look at the same data of the week before to sort of predict these things. And that's what the data would come from if you would want to find such a shortest path. I will explain later in the presentation how to actually solve this kind of thing with Tink. So, graphs. Tink is all about graphs. Now, when I talk about graphs, most people think graphs. Well, we're not talking about these kind of graphs. We're talking about the data structure graphs, which has nodes and edges. And in this data structure, these nodes are closely related to objects, and edges are related to relations among these objects. So I have a couple of examples. Here, for example, you see my family relations, in which the people are nodes, and the edges are the relations among these people, family relation in this case. Whereas I, Wouter, am the son of Renier, and I'm the son of Monique, and Renier and Monique are married to each other. I can expand this by adding my sisters, by adding a sister and a brother of relation, and I can also include other people which are friends of mine in this relation. And this way you can create any type of graph you want. Another type of graph is the Dutch railroad system. In this case, we can model the nodes as railway stations and with the tracks as edges. And in this way, we have a graph of the Dutch railway system. These type of graphs can come in useful when you want to do certain kind of graph analysis, because you can represent real-world data as graphs. A temporal graph. So Pederholm once said, any system with a pairwise interaction and information about time could be modeled as a temporal network or a temporal graph. This basically means that you can model these things with time. So the edges or the relations are not always active. They are mostly active among a period of time. And to further illustrate that, we have, for example, a sequence graph, which you can relate to a text message graph, which represents text messages being sent from one person to another. And a sequence graph only takes into account one single point in time, which is also what you have when you send a text message, because a text message is sent and received at the same time. And we also have an interval graph, which is what Tink uses, which takes into account a starting and ending time of a relation. You could think of this as a telephone network graph, whereas the one user calls another user and this time happens, and the call starts at a certain time and the call ends at a certain time, and in that time the relation is active, and when the phone is hung up the relation ends. So these are things how you can model graphs as temporal graphs. Now when we have time on the edges, we can also think about a temporal shortest path. Now, what is a temporal shortest path? A temporal shortest path is the shortest possible time between two nodes. But we can define short in different ways. For example, we can define short as in the shortest amount of time that we travel, but we can also define short as the earliest arrival time, which means that, for example, when we look at the earliest arrival time from Henk to Tim, we get this path and the time 15, because that is the earliest possible time that Henk will be able to arrive at Tim. But we can also think of a different way, like the latest departure time, which has which is also the same path, by the way, but which looks at the latest time that Henk could leave. And we can also look at the fastest path, which means that, well, what's the shortest possible time that we actually travel? Which is very different from a shortest path when you would look at the amount of edges or the length of edges. And with these shortest temporal paths, we can also make temporal centrality metrics. And centrality metrics are used to look at certain points in the graph which are important or have a lot of influence. We have two different centrality metrics in Tink. One of them is the betweenness, which stands for the centrality. It quantifies the number of times a node acts as a bridge along the shortest path between two other nodes, which translates to when you would take two random nodes in a graph. Let's say, for example, the Dutch railway track, there's a high, the possibility is high that you will travel through a certain station, then that betweenness is high. So when I would take two random points of this graph, there is a pretty high chance that I will travel through Utrecht station if I would take the shortest path among these 2 points. And when we look at the closeness, which is the average length of the shortest path between a node and all the other nodes in the graph, that means that a node is very central in the graph when it's in the middle in this case. So if we take a point, for example, station Hilversum, Amersfoort, or Utrecht, which are all here in the middle, then their average shortest path distance to all the other nodes are fairly similar. But when we look at a node which is far away, such as Groningen, the average time to all the other nodes will be longer. Now, what do we know based on these centrality metrics? We know which nodes have a lot of influence, such that also that which nodes are very important. And Utrecht Central Station is a very important station. If we would disconnect that station, we would have a big problem in the Dutch highway system, because lots of trains wouldn't be able to reach their endpoint. And thus it also has a high centrality. However, this is something that we can see. We can look at the map and we can look at the graph and see, well, Utrecht is a bottleneck point in this thing. But when we have very large graph, or when we have graphs which are so highly connected with lots of edges that you cannot actually see which relations mean what, or they have different values, then it's useful to have some kind of algorithm which you can just analyze it. All right, Tink. Tink is a library on top of Apache Flink. It's the tool that I made. Tink is made to analyze temporal graphs, and it also has the ability to extend the library to write your own algorithms on top of the library to analyze the graphs of Tink. Tink allows for distributed processing. That means that it can be used on different machines and also on different cores to speed up the processing. And Tink is part of the Flink ecosystem. With the development of Tink, we focused on the usability, which means it should be easy to use, it should be easy to implement, and easy to extend. And Tink is written in Java. Tink uses a lot of Flink. This is the logo of Flink. You see a squirrel with a nut, and the logo of Tink is, funny enough, it's a squirrel traveling through time holding a clock, which represents the temporal aspect of Flink. Flink is a framework for big data analytics. It is made for distributed processing in such a way that it evenly distributes its calculations on different machines, and it also, with that comes query optimization to make it fast. Flink stands for fast and agile, and for those of you who know German, where Flink was created, it also translates to fast and agile. On top of that, Flink is open source and has a large community, which is very helpful when you're working on a project. Tink is also open source, so it can also, everybody can download it and create their own code upon it. This is the stack of Flink. On the bottom layer, you see the deployment layer, which connects to different databases. The second layer is the runtime layer, which distributes the streaming data flow and which also handles all the query optimization. And the last layers are the APIs and the libraries. You can see that Tink is on top of the dataset API, which handles batch processing. And there's also a streaming API, but that we don't use. So two parts to the left of Flink, you also see Jelly. Jelly is the graph processing library of Flink. And since Tink is using temporal graphs, which also uses graphs, we also used Jelly. So Jelly is the graph processing library of Flink. It's just as Tink, it's also a layer on top of Apache Flink, and it is made for iterative graph processing. Now, iterative graph processing isn't as easy as it sounds for graphs. So it is made as a way for distributed processing to enable these distributed graphs. For this, we use the signal collect model, also known as think like a vertex, which implements two different functions, the signal and the collect function, to efficiently iterate over a graph. So I want to give a quick demonstration about distributed processing and why it is harder for graphs. So here we have the Dutch map, and every province has a database. And in every database, we have all the people that live in that province. Now, if I want to know the total number of inhabitants of the Netherlands, I can do two things. I can request all the data from all these different provinces, which leaves me with a gigantic database, which takes a long time to count. Or I will send a signal to all these provinces to send me the amount of people that live inside that province, which means that every province will count their own numbers of people, then send that number to me, and I will only have to sum up 12 numbers, which results in 70 million. With graph, this is a bit harder to do because graphs are connected. So if these nodes are on different machines, they still want to communicate with each other. And the signal collect model enables this. So with the signal collect model, we send a signal and we collect the signal. And those signals happen in the same phase for every node, which prevents the communication overhead. And in this model, you can see we have a graph with the nodes 1, 2, 3, and 4, and their related edges. So, and here we can see the different nodes on the different machines, and we see that one has a relation to 2, 3, and 4, in which it signals to. And all these nodes signal to their neighbors, to their neighbor nodes, and once every node has signaled, it will start processing all these messages, and it does it all at once. Then we start the next super step, and we collect all these messages and we process them. And here you can see that node 4 processes the messages that it received from 1, 2, and 3, and 3 only processes the message received from 1 because it can only receive messages from node 1. And this is a very efficient way to iterate over a graph data and still executes all and still be able to distribute the data over different machines. So to further illustrate this, I'm going to visualize the earliest arrival time algorithm. So the earliest arrival time algorithm is an algorithm to find the earliest arrival times at all the nodes from a specific starting node. So in this task, we want to find the shortest temporal path from a source node 1 to all the other nodes in the graph. With this, we have a signal step that looks if the starting edge is larger or equal than the vertex value, and then it will signal it. And in the collect step, we will look if the ending time is smaller than the vertex value, and if that's the case, then we update the vertex value with the edge ending time. In the first step, we will initialize the values. We will set the first node value to 0 and the rest to infinity to ensure that if we set everything to infinity and an earliest arrival time path arrives, it will always be smaller than infinity, so it will update the value. Then we will signal from the first node to all its neighbors, which are 2, 3, and 4, and we will collect the values. When we collect the values, we look if the ending time is smaller or equal than the value that we already have. So the value of 2 is currently infinity. It will receive a 3, which is lower, and it will update the value, and this is what we get. And this is the first super step, and now we move in the second super step, in which we initiate a signal step again. So we take the nodes 2, 3, and 4. We don't process 1 because it didn't update anything. And we will signal it. Node 4 won't signal any node because it's not connected to another node. And we will collect the steps again. And here we see that 1 has an incoming message of 6, but its current value is 0, which is already smaller than 6, so it won't update the value. And 4 has an incoming message of 4, which is smaller than the 5 that we already had, so it will update that value. Well, and then we're done. And on the right side, you see all the vertex values, which represent the earliest arrival times if you would leave at 1. And that is all done in a distributed manner. So, getting back to the use case that we discussed before, we can actually use that earliest arrival time algorithm to calculate the shortest path between 2 points, taking into account this time. Here we have the Dutch highway system in the model of a graph. And if we look at this more closely, we can see that the nodes are the intersections of the highway, and the edges are the highways which are between these intersections. And if we add a time label to it, we can see that how long it takes to get from one intersection to the other, and then from that intersection to another. And then when we would execute an earliest arrival time algorithm upon it, we can see the shortest temporal path between Breda and Arnhem. And that also includes when you leave at different times. It can still maintain the earliest arrival time. All right, then we get to the results and the contributions. So one of our main contributions is Tink, the library itself. It's an open source library that everyone can use, and it's available online, and it's currently also part of the Flink ecosystem, which means it's in the Flink framework where people can actually use it. Um, it's currently the only library available that's written on top of a framework for big data analytics, such as Flink. There are several other of these frameworks, um, which also makes it unique in its way. To test Flink, I created several temporal datasets. And these datasets is also a contribution because these datasets didn't exist yet. And we did several tests with them to test the scalability of Tink, such as how big can we make these graphs in order to still function properly. And we did several parallelization tests to test if it could work also on different machines. And lastly, I will talk a bit about the community impact that Tink had on Flink. So the data sets. So I created several synthetic data sets which grow larger by factorial numbers to test the scalability. These are synthetic, so they're not real, but they maintain the same structure to be able to analyze them better, such that we don't get bogus results. Then I created several semi-real data sets which used graphs that already existed, but they didn't have a time interval. So what was interesting is Tink uses these interval graphs, but there weren't any interval graphs available online, which was weird because it does exist, but the datasets weren't distributed yet. So I created them myself, but these were generated, these intervals were generated, so this was not real data. Eventually, I also made interval graphs based on Facebook and Wikipedia, which actually did work upon interval data, which actually did record so an edge time, which has a starting and an ending time. These datasets were also sent to Icon and Koblenz, which are two distributors of these graph databases, and they also accepted it on their websites, such that these graphs, interval graphs, can also be used by other researchers and by other projects later on. So the scalability tests. We use the different synthetic graphs to see how it would scale up. With this, we use the same structured graph, which grows exponentially by factors of 10. So at the bottom, you can see the amount of edges. It starts with 25,000 edges, then 250,000, 2.5 million, and 25 million edges. And at the timings, we can see that the timings doesn't grow exponentially, which is very good because if it did, it would get slower and slower the more edges that we would add to a graph. We also made the distinction between dense and sparse graphs, in which you can see that sparse graphs are really a lot faster to be processed, even though they have the same size. We also ran tests for the parallelization. For this, we used different cores of a computer, but you can also think of them as different machine in which an algorithm is distributed upon. And in this, you can see that it speeds up fairly fast at the beginning by adding a couple of machines, and later on it converges. So it doesn't gain that much speed eventually after you add 4 machines. This would of course increase if you add actual different machines to a network. But it does show that it works when you add different machines to Tink, that it really gets a lot faster, which is great because that's what we made it for. So the community impact. So during the work of Tink, Flink and Jelly were used. And while I was working on it, I found several bugs in the code. And I also found different things. So In order for Tink to work properly, I wanted to have some things changed in Jelly. These were so-called suggestions, and I also submitted those suggestions, and they were last week. Version 1.3 of Flink came out, and they also processed these suggestions and also the bug fixes, which enabled Tink to be a better library. And finally, Tink also got accepted last week into the Flink ecosystem, which is also a pretty good thing. That brings me to the conclusion. Tink, it's a temporal graph library for Apache Flink. And that's, it's the first temporal graph library which is built on a big data analytics framework. Whereas other libraries and frameworks are mostly built standalone in different ways, and they were also not open source, and they're not really being maintained. Tink had a great impact on the recent development of Apache Flink, as I just discussed, with the bugs that were fixed and the suggestions that were added to it. And during the work, several temporal datasets were created for further research. Of course, there's also future work to be done. So one of the things that can still be done in Tink is the support for multiple languages. Currently, Flink is supported in both Python and Java, and Tink is only supported in Java. Python is a great language if you just want to do a fast data analytics, which would be a great addition for Tink as well. Another future work is the amount of native temporal algorithms. So currently, the Tink supports several centrality metrics and several shortest path algorithms, but this can of course be expanded. There are many more temporal algorithms that can be created, or different algorithms that you can model in such a way to include this temporal aspect. Tink would be better as an abstraction layer on top of Jelly. As you could see in the stack, it's currently an abstraction layer on top of the API of Flink, the datasets API. But this abstraction layer on top of Jelly wasn't possible before because of the way that Jelly was constructed. They have updated it now last week, though. Another addition to Tink would be having it with Streaming Flink. So Streaming Flink is a part of Flink which handles the streaming data, whereas we use the batch data. And with this streaming data, we can look at the different mutations will happen on a graph, and based on that, we create a temporal graph, which we can also analyze further. With that, I conclude my presentation. Thank you for listening. If you have any questions regarding this project or regarding this presentation, please feel free to comment below the video, or feel free to contact me. Thank you for listening. Bye.